So welcome to the Online Manufacturing Summit, and welcome to my shop floor. My name is John Milbury, and it will be my privilege to take you on a quick tour of SOLIDWORKS CAM. My goal? To help you understand what makes SOLIDWORKS CAM different from other CNC programming packages. So if you have a few minutes, follow me and we'll get started. SOLIDWORKS CAM is an integrated 2.5-axis milling and 2-axis lathe programming solution by SOLIDWORKS. You can use SOLIDWORKS to create parts, assemblies, and drawings, and now CNC program at the very same time. So let's open an assembly in SOLIDWORKS that contains a part we wish to machine. SOLIDWORKS CAM is a plugin that can be switched on and off as needed from within SOLIDWORKS. Here we have an existing toolpath for face operation and the rough machining of 3 pockets. Let's review the simulation. Using SOLIDWORKS, let's change the depth of the pocket from 100 thousandths to 250 thousandths. Let's rebuild. And SOLIDWORKS CAM easily updates the toolpath to reflect the design change. SOLIDWORKS CAM stores all the tool and toolpath information directly in the SOLIDWORKS part being programmed. There are no external files to manage. To better understand SOLIDWORKS CAM, let's review the traditional approach to CNC programming used by most CAM programming packages today. First, we visually inspect the part and choose a machining operation to perform, in this case the roughing of a pocket. Next, we measure some geometry to help us choose the appropriate size tool. After that, we select the required faces and edges of our solid model that define the pocket, and then finally we choose machining options such as step over, depth of cut, climber conventional milling, etc. Let's take a quick look at how SOLIDWORKS CAM accomplishes this same workflow. Let's begin by identifying the manufacturing feature to machine and then measuring its geometry. Measuring the geometry provides us with the necessary information to choose the correct tool type and size. Let's choose a 1/2-inch flat end mill and specify the type of operation as roughing and the feature type as a pocket. Next, we can select the geometry to machine. All that's left now is to choose our favorite machining options to get the job done. Let's simulate the results. This traditional method is easy to use in SOLIDWORKS CAM. However, more advanced workflows are available. SOLIDWORKS CAM can automatically identify and capture manufacturing features from a solid model, even dumb models without parametric features. Using patented topology traversal routines to analyze the solid model, faces, edges, loops, and vertices can be collected, grouped, and recognized as discrete manufacturing features such as pockets, threaded holes, bosses, and slots. Over 22 individual features can be recognized by SOLIDWORKS CAM. So let's begin by opening an IGES file of a 3D solid model. SOLIDWORKS can quickly identify and also repair faulty geometry. So to automatically recognize features, we simply tell SOLIDWORKS CAM to extract machinable features. The SOLIDWORKS feature tree now contains the manufacturing features contained in the part. If we select these features, we can see the corresponding geometry highlighted in the graphic window. Automatic feature recognition can remove the drudgery of selecting geometry while CNC programming. But there's something else. Let's spend a moment and measure this irregular slot. We have a depth of 3/8 and a finish radius of 3/8. The length of the slot is 2 inch and the width of the slot is 0.55 inch. SOLIDWORKS CAM stored these critical dimensions during automatic feature recognition. Here we can see the 3/8 depth, the 3/8 finish radius, the 2 inch length, and the 0.55 width. This eliminates the need for the NC programmer to measure geometry prior to tool selection. Now let's take a deeper look at the nature of manufacturing features. Often a single feature can require multiple tools, and each tool requires a separate and unique machining operation. To complicate matters, the machining strategy can vary with part material changes or even when run on different machine tools. A simple counterbore feature can require up to 4 different machining operations. Let's take a moment to understand how SOLIDWORKS CAM might handle the machining of our 5 counterboard holes. We will ask automatic feature recognition to take the next logical evolutionary step in our advanced workflow, and that is requesting it to automatically generate our machining operations and tool paths. As expected, automatic feature recognition was able to recognize 5 different sized counterboard features in our part. As requested, machining operations and tool paths were also created. These 20 operations can be sorted and reordered in our tree based on like operation and similar tool type. In addition, we can combine similar operations that share the same tool. Let's take a moment to review the results using our toolpath simulation. First, our spot drill, and then our drill. Next, the milling for the counterbore. And finally, the chamfer milling of the counterbore. For advanced automated workflows, feature recognition is necessary, but not sufficient by itself for comprehensive automation. By utilizing a rules-based technical database, SOLIDWORKS CAM has the ability to associate manufacturing features with a company's preferred machining strategies. The recognized feature and corresponding dimensions are passed to and processed by our rules-based TechDB. The coupling of these two technologies result in decreased programming time, the capture of manufacturing intellectual property in the form of machining best practices, consistent high-quality G-code, and overall reduced lead times. Let's review the rule that auto-selects the flat end mill that will rough and finish the bore diameter of our counterbore hole. I've chosen to use an expression based on the bore diameter value that has been passed to the TechDB. I've asked the TechDB to search my existing tool crib and select a flat end mill whose diameter is between 60 to 75% of the bore diameter. This is the ideal tool diameter when utilizing volume mill high-speed machining to rough and finish the counterbore diameter of our feature. Now let's review the rule that defines the machining depth of my center drill operation. I have defined a rule that states the depth should be automatically calculated to achieve a spot diameter that is 90% of the drill hole diameter. In the video, you can clearly see that the spot diameter varies for our various size counterbore holes according to this rule. With a basic understanding of SOLIDWORKS CAM under our belt, let's program a real part and witness the power of integrated CAD/CAM working together. Let's use the convenient SOLIDWORKS design library to retrieve the vise we will use to hold our part during the machining process. Our vise has an associated drawing that will be used later to communicate the proper setup to the shop floor. The SOLIDWORKS multiple document interface allows us to easily drag and drop our part between document windows. Setting our part to the proper height in our vise is a snap using SOLIDWORKS assembly mates. We can easily size our stock to actual purchase dimensions using the power of the SOLIDWORKS API and our AutoSize macro. Let's isolate our part within the assembly and drag it to the proper XY location of our stock boundary. Note that our stock size is 3 inch by 3 inch by 1/2 inch, not the irregular bounding box sizes that are calculated by other CAM programs. Let's check the availability and pricing for our stock online. As we can see, purchasing a 36-inch length will give us a raw material cost of about $2.50 per blank. Next, let's delete the extra tail-on grips that we won't be using. And now is a great time to revisit our drawing and check on the updates that have occurred. I want you to notice that our part is properly positioned, the raw material size is called out, and the bill of material is updated to reflect the correct parts and quantities. Now, because we are programming assembly, we must identify the part or parts to be machined. Next, we create a setup and identify the machining direction in Z. And we can easily direct the stock manager to utilize our 3D wireframe sketch as the material boundary. And finally, we can select any SOLIDWORKS coordinate system as our XYZ machine 0. So we're now ready to begin creating toolpaths. To machine the outside of the part, we can start by interactively selecting a part perimeter feature. For the machining depth, we will specify the bottom of the part, leaving 1/8 inch of stock material. Generating the operation plan directs the TechDB to select the required tools and apply the default machining strategies for each feature. This results in a rough mill and a finish contour mill operation being added to our operation tree. We can now generate the toolpaths for these two operations. Although a great deal of automation was used in this workflow, I still have complete control to override or modify the results. Let's review the elapsed machine time for this rough operation and see if we can improve upon it. Let's change tools from a 1/4 to a 3/8 inch diameter end mill. We can also change our machining pattern to volume mill, high-speed machining. The volume mill can also automatically select my spindle speed and feed rates. After previewing the toolpath, I can now see the decreased cycle time due to my changes. Next, changing the finish contour operation from a 1/4 to a 3/8 inch diameter end mill is easy to do by simply dragging and dropping. After this, the toolpath is automatically rebuilt. So let's simulate our toolpath and view the results. Note the 1/8 inch carrier stock left on the bottom of the part. Now it's time for a full frontal assault using automatic feature recognition. A moment ago you saw me interactively recognize a feature and create two operations. Now using automatic feature recognition, we were able to recognize the remaining 11 features and generate an additional 20 machining operations, all in a matter of seconds. The operations can be easily sorted by a number of criteria. In this case, a simple sort based on an operation list order schema is all that is needed. We can also dynamically reorder our operations in the tree using standard Windows drag and drop functionality. Let's place our 3/8 inch end mill roughing and finishing operations back to back. Next, we can combine similar operations using the same tool on the entire tree, or we can limit our scope to just a few operations. Here I will combine the separate rough pocket operations into a single operation. We can also rename our operations by slow double-clicking the operation name. Before we run our simulation, we can include our vise, our jaws, our grips, and this will help us get a more accurate simulation and a better understanding of any collision that may occur between the tool and our setup. If we do experience a collision, it will appear as a red color during simulation. Now let's zoom in to get a really good look at our toolpath simulation. The tool cutting sequence is in the same order that appears in our operation tree. We can now compare our simulation model against our solid model and check for undercut or overcut regions. The green color you see indicates the tool paths are within tolerance and we have a good part. It's now time to post-process our tool paths to create G-code for the machine tool. SOLIDWORKS CAM allows us to select the appropriate machine and associated post-processor. Detailed information regarding the post-processor is available to the NC programmer from within SOLIDWORKS CAM. The Posting tab contains questions from the post-processor for the machinist to fill in, such as a unique program O-block number to be used in the G-code file. Our technical database stores the critical machine tool specifications. Important information such as the type of machine, the rapid traverse and cut velocities, the maximum spindle speed and horsepower, the number of tools that can be held in the tool changer, and the average time it takes to change a tool. A simple right mouse button on the setup in our tree initiates our post-processor. During posting, each line of G-code is displayed in a scrollable window. After posting, this window can be scrolled and used by the CNC programmer to review the newly created G-code. However, most programmers opt to review the code in our SOLIDWORKS CAM NC editor. Now, this editor allows programmers to efficiently modify G-code when required. Search functions allow us to quickly move to each tool change, and advanced editing functions allow us to renumber, auto-insert spaces, and globally adjust spindle speeds and feed rates. The backplot capability allows us to check for stray toolpaths that could affect part quality on the shop floor. And finally, we can review in-depth machining statistics. SOLIDWORKS CAM allows the programmer to create a setup sheet that contains information for the CNC machinist on the shop floor. This can be as simple as a text file or a stylized HTML page. These setup sheets can be customized to include information such as machine details, setup origin, the controller, estimated machining time, part material and stock size, operations, feeds and speeds, and of course tooling information. In this example, we will create an HTML page of just our tooling used in the program. Let's come back and revisit the progress made on our SOLIDWORKS drawing. Post-processing metadata has now been automatically updated in our title block. Let's use the SOLIDWORKS Custom Property tab to add the remaining title block information. Now let's take a close look at our bill of material. SOLIDWORKS keeps our entire set up to date with the proper items, description, part number, and quantities. Let's take a quick look at our notes instructing the operator where to zero his machine and which offset number to use. Next, we're going to do a little housekeeping here. And now we are ready to produce yet another option for shop floor documentation. SOLIDWORKS has the ability to create a lightweight 3D version of our 2D setup drawing for viewing on the shop floor. Our free lightweight viewers can be installed across the manufacturing enterprise. What I love about this format is that the 2D drawing also contains a 3D solid model, which can be animated and interrogated, and then finally printed on the shop floor if a hard copy is needed. So I want to thank you for attending today's presentation. I hope you enjoyed this as much as I did in presenting it. There is so much that wasn't covered in this short video. Please take a moment to visit solidworks.com/product/SOLIDWORKS-CAM for an in-depth understanding of all the SOLIDWORKS CAM offerings and how we can help your company enter the brave new world of smart manufacturing. Thank you, and I hope to see you soon.